Classification regression trees are typically models. They've been around for quite a long time. One of the most famous of them is CARET strategy that Bryman and a bunch of people published on in the 80s. So using CARET as an example, it basically forms a decision tree by first looping through all of your data, every value of every predictor in your data, and trying to find a split of one of those predictors that maximizes some criteria. Maybe if you're doing regression, it minimizes the root mean squared error of the predictions, or if you're doing classification, it tries to have resulting classes of your outcome that are most pure and so on. So what a classification tree does, and I'll show an example in just a minute, is it basically splits your data into two groups, and then within each of those groups it splits the data again based on a similar sort of searching criteria. And it keeps splitting the data until basically what you get is you get a set of like nested if-then statements. So when you make a prediction from a classification or regression tree, you have all these conditional statements. If the square footage of my house is greater than 3,000, then and if the number of bathrooms is less than 2, then your let's say the price you would get on a house if you sold it would be on average whatever the amount is. And so they're nice models. But they basically partition your predictor space into rectangles. And that's good and that's bad in some ways. And again, I'm going to talk about the data that I'm actually going to just use as to illustrate things. And then I'll show you how, for example, a CARET tree or regression tree would work on that data. So I found this data set. I don't remember how I found it, but this one piece of software called Spatial Key, which I don't know anything about, posted some data on their website, and they had a couple hundred almost 1,000 real estate transactions. So they had the sale price of houses with a fair amount of information about the houses, the address, everything that the Sacramento Bee newspaper had captured. And they were using that, plus they had geocoded them. So it was kind of an interesting data set. So I thought, well, maybe I'll try to use that to illustrate models and things like that. So I took this data and so I have this R package called CARET. So it's not in the current version of that, but it's in the version that'll be next on CRAN if you want to look at this data. It's amazing how many errors you find in the data. So Google is surprisingly good at telling you the sale history if you know somebody's address. So there are tons and tons of things that I enlisted my daughter a little bit and filled in missing or data that was clearly not correct. So that's the data I'll be using. What I did was, in the next version of CARET, you can load it. It's called Sacramento. And when you look at it, there are a bunch of, well, first the outcome would be price. So this is in dollars. There is the city that it was in the zip code, which are probably pretty similar. The number of bedrooms, number of bathrooms, the reported square footage. They had in here the type of house, which only had 3 different levels. You can see 2 of them there. And then you can see longitude and latitude. So, one might say, okay, can I predict, based on all these things I know about a house, can I predict what its sale price would be? Okay, and that's what I'll use as an example for the talk today. And again, you can get to this data. It's in GitHub right now, but it'll be in the actual package on CRAN soon. So what I did is I ran up 20% of that data and held it out that I'll use for evaluating models as a test set. So I'm not really going to touch that until I feel like I pretty much want to know what the model does. And then I took the other 80% and held it back, and that's what I'll be building models with and showing you a lot of. So again, since this is our users group, I should show you some R code. So I set the seed so you can reproduce everything, and then I take the data and use this create data partition function, and that splits everything off, or at least tells you what should be, let's say, in the training set. And then I create 2 data frames, one's training, one's called test, that have the data that I will use the model with, and then the data I will use the test with, and you can see the relative number of data there. R is great at doing maps. So what I did was I did a little ggplot magic, and here are where all the houses are based on their longitude and latitude. So the red data are the ones, the 20% that were held out for training, or I'm sorry, for testing, and then the blue is what I'll use for training. This doesn't really mean anything, I just thought it looked kind of cool. So, right. So okay, so let's say we were to fit a regression tree on this. So if you take the training set that I have here and you do just one iteration of splitting, what happens is the classification, or the regression tree will search through all of these factors and try to split on one of these values. And so it might be, hey, if I take my zip code, it seems like it's important. I might say, okay, if these zip codes were in one group and those zip codes were in another group, how well would a model do if I predicted the average price based on that sort of partition? And again, it goes through all possible partitions and tries to figure out what works best. And so in this particular case, you can see what it does is it picks a square footage of the house, and if you're above, let's say 1,600, here's the distribution of, and this is on log 10 scale, so sale prices of houses on that side of the split, and then this is about 300 on that side, and then if you have a smaller house, you can see that proportionally you have lower sale price, which makes sense. Now, this isn't an especially good model because there's only two possible predicted values. But what CARET would do, for example, is it would go on this side of the split, on what's labeled as node 3 here, and then do the same thing. Within those 321 data points and the data I have for them, what's the best split of the data to then, again, provide the biggest difference in the sale price between those nodes. And so you can see what happens is I had to monkey with the output here. There's 29 zip codes that it splits on one side and another 29 that are on this side. For the smaller houses, interestingly, it also splits on zip code here. And so you can see it start to differentiate the distribution of prices in the terminal nodes here. And then if you just let it do its thing, and it builds a tree out as far as it can, and then it does this pruning algorithm that prunes it back. The final tree that you get here is, let's say, 2, 4, 6, maybe about a dozen terminal nodes. You can see it splits on zip code here and square footage there. And then when this particular model, you get a prediction for a new house. You take your house that you want to predict, run it through these if-then statements that are signified by this model, and then you take, let's say, the average log 10 sale price within the terminal node, and that's what your prediction is. And that's kind of how trees at least work usually. There's many, many different types of trees, but that's the basics of them if you've never heard of them before. So the good thing is, I don't know that it's really true of this, but people always count trees as having really simple interpretations because they're just a few if-then statements. It's kind of inflated to me because if you have any amount of data, the trees tend to be really, really deep. And for me, it's not really that instructive to know that I have, in this split, I have 28 zip codes here and 29 zip codes there. I don't know, that really helps me interpret anything. So they theoretically could be interpretable. In this case, I wouldn't say that's the case. But they aren't really fast, even though you're doing a bunch of exhaustive searches of your data. The math involved goes really quickly, so they're really quick to fit. What's also cool is they have built-in feature selection. So if I have a bunch of predictors in my data set that I never split on, functionally my prediction equation is independent of those. So it's like they never existed to the model. And so I've done both feature selection and like machine learning in this particular one step, and that's a great thing. However, they're known to be unstable, meaning that if I change the data a little bit, if this first split changes because the data got moved around a little bit, the whole rest of the tree could be very different. And that's generally not a good thing, but some people, I'm not going to go into this too much, but people learn to exploit that for good, basically, by doing ensembles like random forest and boosting and things like that, which you couldn't really be effective at if you didn't have this instability in this particular model. So, the good news is trees are fast and usually pretty simple. Most of the bad news is, they're maybe not the highest performing models and they're a little bit unstable. The thing that I deal with a lot of times, because I have a lot of regression problems where we're trying to predict a number, is that they also don't do well in the extremes of the outcome. So here's a different data set where I plotted for the test set, I have the observed by the predicted values. And you can see at the high end, it under predicts, and at the low end, it also under predicts. And so the reason for that, the reason why a lot of trees don't do well in the tails, is if you look at the terminal nodes here, like for this one, if I'm going to form a prediction, it's going to be the average of these data, right? So there's no way I'm ever, even though my training set has data that go much higher than that, I'll never predict from my model anything that's above the highest average terminal node distribution. And so they don't do well in the tails because they've kind of shrunk the predictions in towards the mean a little bit, right? And that's a consequence of what's in the terminal nodes. When we estimate our predictions from these terminal nodes, we generally take the mean, and that's why you get a situation like this. And this is a random forest model. So, their R squared might be great, but the root mean squared might not be that spectacular because you have these large errors in the tail. But the correlation is really tight. And so sometimes you don't really see this as a phenomenon, but if this is the area that you care about, the low values, the high values, it's especially painful because you want those to be the most accurate predictions. Okay, so keep that in mind because the methods I'll talk about are sort of do better at this than most tree-based methods. All right, so this is Guy Ross Quinlan, and he wasn't, he wasn't one of the original people who developed classification of regression trees, but he was sort of that era. He published after a lot of those people, but he made a bunch of really interesting and important sort of advances in tree-based models. And so he published a lot in the late 80s and early 90s. He published a lot about the rule-based models we'll talk about, but then he just kind of dropped, from what I can tell, just stopped publishing on things and just sort of dropped off the face of the earth. So a lot of the things that he's done haven't been as well known as, let's say, the whole CARET crew that's out, is at Berkeley and Stanford and things like that. And I think that's just because his rate of publications went a lot down. I don't know why. He also continued to develop the models that he had. So the models that I'll talk about today, they're interesting in that we have the original publications as to what they did, and then maybe like a 15 or 20 year period where he had closed source implementations that he sold through a company, which is fine, but we never really knew what they were doing. We don't know how well they aligned with the original publications. And then a few, let's say that's like 5 years ago, 6 years ago, he open sourced all of his models. And so it was kind of cool because we got to dive into them, thousands of lines of C code that was like written in like the 90s, and see what they were actually doing compared to what we thought they were doing and what was published. And so that's a lot of what I'll be talking about today. So he came up with this thing called a model tree. And the idea behind a model tree is you build basically a tree, but in the terminal nodes and in other parts of the model, you don't estimate the predictions using just the average of what's in terminal nodes. You actually build a regression model on the data that's in the terminal node. And because you're building a regression model, you don't have that regression towards the mean of the predictions that I showed you with the trees. Okay, so the one he originally came up with, he named his models interestingly. This one was called M5, which I assume to be the 5th iteration of things he was trying to do. And it's different from what you would get from a regression tree in a few different ways. The splitting criteria is different, but a lot of his models tend to use different splitting criteria than the CARET family of models. The terminal nodes predict not only by the mean, but they develop a regression equation for the data that's in the terminal node. And then he also has a smoothing idea that actually, I'll talk about that in a minute, but as I'll show you in a second, he builds many different linear models as a tree gets built, and then he averages them, does a weighted average of them. So he does not only regression models in the nodes, but he has multiple regression models that he averages. So it was kind of an interesting way of doing this. So software-wise, for a long time, the only thing that I could find, open source especially, that did this was what they called a rational reconstruction in Weka, and they called their model M5 prime, because I think they felt like, they couldn't say it was M5 because they weren't exactly sure what the details were. So for a long time, M5 prime was really the best, or one of the only ways you could fit these models that I knew of. And that's in Weka, in R1. And again, if you have questions, I want to make sure I get through this, but if I've lost anybody or admitted something, feel free to ask. So I'll show you the structure of a model tree. So it does this thing where it figures out, exhaustively looks through the data, and it figures out what to do for a split, right? So the first split in my regression tree before was square feet, okay? So what it does at that point is in the terminal nodes after each split, it builds a regression model on the data that's in that terminal node. And it uses any predictors in the data set that were involved in that split or any split above it. So in the first split, if I split on, let's say, square footage of a house, the terminal nodes would be a model that is basically, the outcome is equal to, an intercept plus a coefficient times the square footage. And let's say the next split on is number of baths. So the second terminal node, or the second node I would get as I split down that path, the linear model there would be a function of both the number of baths and the square footage. So as I accrue things that I split on, those are potential predictors for the terminal node models. Okay, yes, question?
So, Max, if you know that after the split you're going to fit some, for example, a regression model, so is that taken into account in how you make the split? I want the two sides to be predicted best by a linear regression as opposed to getting a split. I mean, that can be different, right? As opposed to getting a good split.
So every time, not every I can think of a few exceptions, but most methods like this are, well, they're greedy. So they don't go back and reevaluate things. And each split is almost always done in isolation of everything else.
Right.
Right, so it doesn't know that this split over here, if this split over there was done slightly different, might make a huge improvement. So they're all autonomous, like in a vacuum kind of splits in the regression models. He does do a lot of interesting things. I don't mean that as a pejorative statement, but things I never would have thought to do, because his code's fairly efficient, where he will try at some point to do global optimization of things. But along the path of creating the model, that doesn't happen too much. Okay. And once you see what he does with all these regression lines, I'm not sure it would make that much of a difference. Okay. All right, so much like a regression tree, he would keep going until he gets to some point where he doesn't feel like he has enough data to keep splitting. So you run out of data and you kind of stop there. I'll get to the note there in a second. But schematically, here's what it looks like. So the first split, that results in two nodes, and I call them model 1 and model 6. Model 1 is a function of the thing that was involved in the first split. And then when I go and split model 1 again, on whatever variable I come up with here, model 2, first you don't get rid of the linear model from model 1. Model 2 is a function of any predictors that were involved in this split or this split. Okay, so at the end of the day, in this particular case, there's 8 models because there's 8 terminal nodes. Well, there's 5 terminal nodes here as terminal, but along the way there were a total of 8 terminal nodes that were formed along the path of making the model. So there's 8 regression models that get created, okay? So what he does is, he's smooth. So it's funny, when you look at the code, so Pfizer uses Cubist a lot, and we had bought the source code for it because we use it so much, and we wanted to try to see if we could optimize it and things like that. And he sold it to us, and he said, well, yeah, you can look at it, but don't talk about it. And we're like, okay, that's cool. But when we were trying to figure out what it was doing, he had a little note, and he said, he had a function that said, Pregabon smoothing. That's all the comments said. I'm like, what the hell was that? And so I knew there was a statistician who was at AT&T named Daryl Pregabon. So I was like, Googled like his stuff in smoothing. I couldn't find anything. And then I was talking to Quinlan years later, and I said, okay, what's Pregabon smoothing? And he said, oh, well, Trevor Hasty and Daryl Pregabon wrote this technical report when he was at AT&T, when they were both at AT&T, about smoothing series of models. And he just took that, and that's where he came up with this idea. But it's just funny, it's just a comment in C code. So to figure out exactly how that happened, I don't know. But what he does is, at each step of the way, this is some math here that basically says each prediction at each node is made as a function of the model that you're at and the model that came before it. So kind of going back here, if my new sample I want to predict winds up here, in this terminal node, you go down that logical path and you get here, the prediction for that sample comes from this linear model and that linear model. And it has that equation I just showed you a minute ago, uses a way to smooth them. Basically, it combines them in a way that has different weighting. But it's a linear combination of linear models. So in itself, it is a linear model. But if you have a tree, a model tree that's like, 50 splits deep, you're averaging at any point along that path, let's say 50 models. So it smooths the crap out of the predictions. And that's one of the reasons it works so well. And it's also one of the reasons why I think any global optimization thing here would just get obviated because of all the smoothing. One note I want to make, and this is kind of a separate topic, but it's worth discussing, is these models, when they split, let's say you have a factor like zip code. As you may have noticed in the first tree with CARET, it doesn't need to split up the zip codes into dummy variables like most models would need. It doesn't need a numerical representation of categorical data. So like CARET and a lot of other models, when you do splits with a model tree, it has the ability to say, okay, I'm going to put 2 zip codes over there or 48 over there. It doesn't create 50, let's say you had 50 zip codes, it doesn't create 49 dummy variables and treat them as if they're independent data. You can do that. In fact, I do it both ways in these slides. But it's worth noting that if you want to treat categorical predictor data as categorical predictor data, this will do that. And it's actually fairly efficient in a way that it does things. Okay. All right, so again, each prediction, the parent here is a function of the parent's model and the child's model, and then I don't remember the original paper, but it tends to work pretty well. Another thing I didn't mention is, like CART trees, what the model tree does is it builds a really, really deep tree, and then it has a pruning algorithm that tries to prune it back so it's not as complex. Because the idea is, as the trees or model trees get really, really deep, they tend to overfit the data. And that's generally true. And so most of these methodologies have ways of internally sort of pruning back the complexity of the tree, and model trees do the same thing. So for the Sacramento data, when I fit a simple model tree on this, the original unpruned tree had 81 paths through 81 terminal nodes, so there's 81 distinct logical paths through the tree. But when it did the pruning algorithm, it tuned that, or it turned it back to 2 paths. So it went from a tree that had 89 terminal nodes, but it pruned it back all the way to 2. So the pruning here did quite a lot in the process of doing that. Okay, so that's kind of the structure of a model tree. Now, the name of the title, or the title of the talk is, rules, rules, rules. So another thing that Quinlan did that to me was really interesting is he's one of the big people that I think started to really develop how you can develop rule-based models, but also develop them from trees. So let me talk about trees and rules for a second. So again, as I said, tree-based models are basically nested if-then statements. So if I had a tree that had 2 splits and had 3 terminal nodes, I could write that down like this. And if the first, that's supposed to say x1. If x1's greater than 1.7, and if x2 is greater than 202, then you would predict the outcome to be this. Otherwise, if it was less than 202, you would predict it to be this. But if x1 was less than 1.7, you'd predict it to be this, right? So those are just if-then statements.
Quick question.
Yes.
Does it have to be linear models? Could it be nonlinear regression, like Poisson regression? Or...
Sure. I mean, that's not how we did it, but there's no reason why you couldn't do that. There are other papers that I've seen where people do that. They do survival models in the terminal nodes and other things. So yeah, sky's the limit. Go crazy. So what we can do is we can take these if-then statements and treat them as if they're not nested, right? So the representation that's at the top or here, this is the same if-then statements, but I've just flattened them out. So if I use this code, it's the same as using the code before because my new sample is only going to go through one path, through only one of these statements. Okay, so this is an equivalent way to represent the nested if-thens of trees, but I've just sort of flattened them out. Okay, so these would be rules. So one rule would be the first one, or let's say the last one. If x1 is less than 1.7, then I should predict it to be 2.5. And so what Quinlan did is says, well, we can prune rules because there's probably a lot of redundancy in these rules. And so he came up with algorithms similar to how trees prune themselves and figured out ways to add or remove conditional statements or rules entirely from a set that was maybe defined by a tree and get a better model by doing that. Getting something that's more parsimonious and hopefully predicted with the same amount of power. Okay? So again, you don't have to create rules like this, but if you have a tree, it's already a set of rules. So you could then try to prune it in a different way and simplify it in a different way by treating them not as nested.
Quickly, the pruning method is kind of based on cross-validation, or?
He doesn't do it that way, but other people do. So, so CARET trees have an internal cross-validation where they use this one standard error rule where they internally cross-validate the model, which means you kind of refit the model a bunch of times. He has this thing he calls pessimistic pruning where what he does is he looks at what the error rate would be with and without whatever part he was thinking about pruning. And he does some, and he even says in his book that, you got to take these calculations with a grain of salt from a pure statistical standpoint. But he tries to look at like error bounds. Like, I can't remember exactly how it works, but it's something to the effect of, is me reducing the complexity of this tree within the error bounds of what I would see normally. And if it is, then you would get rid of it because it's there's no statistical difference between a tree that has, like, say, 10 nodes and 9 nodes. And so the value of that, it doesn't have to refit anything. It's very fast. Again, the statistical nature of that, as he says, is not. I mean, neither is the one standard error rule. But you would look at that, and you're not doing like a bunch of like binomial tests or anything like that. But it smacks of that, which the assumptions there would be obliterated. Right? So it's not. It's the cool thing about machine learning is you can do things that violate first principles of statistics. But if they are proven with validation data and things like that to be very effective, then sure, why wouldn't you do it? And this is one of the situations. All right, so So in the model tree I fit, you could take one path through the tree, and it looks like this. We have square footage less than about 1,600. If the zip code is not in this group of about, 49, if the number of beds is less than 2.5, less than or equal to 2.5, and then you see a bunch of things about latitude apparently is very important when you're predicting here. So you see a bunch of rules for latitude. Well, I mean, you could certainly look at this and say, well, geez, we have, 5 terms involving latitude going either direction. We could probably simplify that a lot. So another thing that you do by pruning these rules is you can take something that is probably logically more complex than it actually needs to be. Okay, so in the model tree that we already fit, if you look at it from a rule perspective, there's a lot of redundancy in this rule. So people do trees or rules from trees in different ways. One way to do it is called separate and conquer. And so what people do sometimes is they'll fit like a standard, let's say, regression tree, and then what they'll do is they have this idea of coverage, and that's the number of samples in the training set that are covered by that path through the tree. So what separate and conquer does is it builds a tree, and then it figures out the coverage of each terminal node, and it takes the one that affects the most samples in the training set, and it saves that path through the tree as a rule. Okay? So then it takes those samples out, and it fits a new tree, and does the same thing. So it doesn't take the entire tree and break down the rules. It basically derives one rule from a tree, and then it removes data affected by that rule, and then fits another tree and finds the best rule there, using the same criteria, and so on, until it gets to the end, until it gets to know more data. So that's one way of constructing rules from trees. Yes?
So just to know what you said, the second tree is made off of the rest of the data. You take one sample out and you predict, and you've estimated it.
Yes.
And then you take the rest of it and you put a new tree to that?
Yeah, so if you had 1,000 data points in your training set, and the largest rule covers 200 of them, you take that path out, take those 200 samples covered by that rule out, and then fit the next tree in the 800, and just keep winnowing it down that way. Yeah. So what people will do sometimes is they will basically, when you get a new sample, they find the one, so it might hit multiple rules, right? And so they say, well, the best rule is the one that covers the most data points. So then most rule-based models would then say, okay, we'll make a prediction using one of the rules, and the one we'll pick will be the one that has the largest coverage. And so that's a lot of what people do with rules. Yes?
They can't, these rules wind up contradicting each other?
They can. Yes. So, the way the algorithm would resolve that is the one that covers the most samples wins. Which, you could, there's ways you can think about it. I think the idea is the more data, the theoretically higher quality of the rule. All right, so I also wanted to show for the model tree that we fit what the terminal node would look like. And so, you split on, remember before pruning, there were 81, I think, paths to the tree. So, whatever you split on the path to that terminal node, this is an example of one of the terminal nodes. And you can see zip code is represented a lot there. So zip code was used in a lot of splits. City was used once. So, these are kind of like collective dummy variables. So if your city is in this long list, that has a specific coefficient associated with it. And then zip code impacts the linear model in many different ways with different subsets of linear models. And then you can see bed, square footage, longitude, latitude, and all that. Okay, so this is what a terminal node regression model might look like. And actually, he does some, it works, but things you would cringe at if somebody said they did this in a regression model. He does some things where, based on absolute errors and some other things, where he prunes each regression model using not a stepwise strategy, but some heuristic strategy that I think if somebody told me what they were doing, I'd fall over. But it works, so I can't complain too much. So anyway, so that's an example of what a terminal node might look like. So I did some cross-validation for this, and what I decided to do is I decided to fit the model a bunch of different ways. And so, in this panel is when I represent the zip code, the city, and everything like that as a dummy variable. And here's where I let the model tree figure it out by splitting factors in the way that I showed you before. So this would be what it would look like when I use factors. So I let the model split into groups. Whereas dummy variables, it would be like zip code, 95820 would have its own coefficient. Okay, so that's sort of the difference between these two panels. And then the red line here are models that have been pruned. In the bluish green line here are models that aren't pruned. What you can see is, we want root mean square to be low. So if you don't prune, whether you smooth the models or not makes a big difference. So smoothing really reduces the overfitting because you're averaging over a ton of models. But if you're going to prune your tree, it doesn't really matter too much if you smooth it or not. Okay, and that kind of makes some intuitive sense. So, depending on what's faster, you want to do at least pruning or smoothing by looking at this. And in this particular case, this is a whole nother talk I have in the can. Factor representations of the categorical data do better than encoding the categorical data as dummy values. So, yeah. All right. And if you were fitting this in R, again, this is about R, so let's talk about R. You load the R-Weka package, and then you use the M5 prime or M5P package. The only thing I did that was different is, by default, it won't split if the number of data points in the terminal node is 4 or less, and that, to me, seems excessive. So I bumped it up to 15. So if you want to fit the full tree where it does the pruning, the smoothing, the whole gamut, that's the code that you would use, very simple. If you wanted an unpruned tree, there's some different options. You can give the control function, and the n, I don't know why it's called n, but the n function controls the pruning. And oddly, if you make it true, it does not prune.
Okay.
Yes?
But I take it, does taking the log of the price make that much of a difference in this model?
Yeah, price is pretty skewed. So, if you're fitting your regression model, what will happen is the model will try to optimize on the residuals. Yeah. And so, if you have a really expensive house, the residual is probably much larger proportionally than a smaller house. Yeah. So, it's kind of shows that that's a good idea, because when I look at the box plots here, these are log 10 units and they're nice and symmetric. Yeah. So this is a classic case of logging your outcome is probably a good idea. Now, I should say, for a simple tree, it probably wouldn't make a difference, because you're doing splits of the data. I mean, it would drag your mean up a little bit, but it probably wouldn't have the impact that a model that fits linear regressions, many linear regressions would have. All right, so and then this is a little more code where, if you want to tune these trees and tune them over whether the rules are pruned or and things like that, and produce a plot that kind of looks like this. You can do that using the CARET package, and there's the details there. The nice thing about this is it fits the models a lot, but it uses cross-validation to figure out what the right amount of smoothing or pruning should be in your models, if any. So there you go. All right. So there's this thing called Cubist. So Quinlan, when he open sourced, he didn't have his M5 model open source. He had this thing called Cubist. So we were like, we know it's kind of like a model tree, but we don't really know a lot about it besides what he had on his webpage. And so what's kind of cool, both for this model and for the C50 model, I kind of feel like we got in luckily just at the right time, because we like these models a lot. And literally, as we were writing the book, he had open sourced these things. And so not only do we get to really be some of the first people to comb through the source code and say, okay, what exactly is this thing doing that we've been using all these years? We were also, in the book that we wrote, we were able to really publish what that stuff does. So in some of the things I'll show you today, you're going to look at some equations and maybe scratch your head and be like, what's that do? And I don't know. I can just show you what's in his code. And in many cases, so we actually, since we had so much of his work in our book, we had him as a reviewer. And so I was really particular to send him that chapter and make sure that I'm getting the equations right. And sometimes he would look at the equation and say, well, you could write it that way, but if you write it this way, it's a little more intuitive. But then there are some equations, like one I'll point out later, that he never said, and I have no idea why it's doing what it's doing, but I can tell you it works pretty well. So it's like, somebody gives you a long equation and you're trying to backfit, why do you do that? And sometimes you can do that, and other times you just give up. So what's different about Cubist than a model tree? Okay, well, the first thing is the techniques it uses for smoothing, creating and pruning the rules, are in some cases slightly different, in some cases are really different than what I just described. He also has a boosting-like procedure. He doesn't call it boosting, and it's not really boosting, but in actuality it's really similar to boosting. So that's another component that you can use in these models. And then he does, this is like an ensemble model. He has this thing I'll show you in a minute where you get a prediction from the model, And then if you tell it to, it can go back to the original training set and almost do a nearest neighbor fit and adjust the model predictions using the actual training set nearest neighbors to the data point that you're trying to predict. So it does some really interesting and cool and effective things that I never would have thought of doing. And that's sort of what differentiates it from model trees. So let's talk a little bit about this. I should say that there's this guy I work with who's a fantastic computational chemist named Chris Kiefer. And I went through all the C code and figured a lot of stuff out. But Chris is the original guy who had to use this code on a daily basis when we bought it from Quinlan. And you know, if you want to know where the bodies are buried in that code, like Chris can tell you that. I can do a pretty good job. I can tell you what zip code they're in, but Chris knows everything about this. So he and I have many discussions, so we're really grateful for him. All right, so first thing is separate and conquer does not happen in Cubist. What it does is it fits, like I showed you originally, it fits the entire model tree and then it just flattens the rules. So all the rules come from one original tree. There's no iterative creation of rules. Okay, so that's the first thing. The pruning and smoothing, they're not worth me really talking about the difference in pruning because it's a lot of minutia. But you know, previously we had this nice-ish formula for smoothing. That's how we get at any particular level of the tree. This is the equation that shows how you average the current level with the one before it. And don't forget, the one that comes before it is also a smooth model, so it's recursive kind of smoothing. So that's the equation in M5. This is the equation in Cubist. So it's a linear combination of the parent model and the child model. And these equations are right, but I don't know why that is. I don't know what this is doing. In fact, sometimes this can be negative and get set to 0, I think. So, so this works, and I've tested this against M5 and tried to control for as many other things as I can to see that they're equal. I have seen some improvement on doing this. It's not a crazy, like 20% of performance by doing this smoothing as opposed to the other smoothing. But what I've come to sort of respect when you look through his C code is I get the impression that he gets an example that contradicts what he's been doing and figures out how to make that work along with all the other examples that maybe he's ever run. So this model seems like a really curated model. So I have faith enough that whatever this equation is supposed to be doing, it's doing it well. And I don't know why it's doing what it's doing, but it's worth showing people. So the smoothing is different. All right, so we'll stop there for a second. So if you just wanted to fit a single rule-based Cubist model, then we took the C code that he had and made an R package out of it. So it's called Cubist, and if you want to do the basic old Cubist model, it's really simple. You just give it a matrix or a data frame of your predictors, and you give it your outcome, and then it does its thing, and we have predict methods and some plot methods. The summary method is what actually shows you the outcome. And I've abbreviated here. So here are the first two rules that Cubist shows you. So the first rule, and again, these are after pruning and smoothing. The first rule is based on zip code and the number of beds. So if you're in these zip codes that are listed here, and you have less than or equal to 2 beds in your house, then here's the linear model. This is the final smooth linear model that you get, and it's a function of longitude, square footage, and beds. Now beds is in the rule, and zip code is in the rule, but longitude and square footage are not. So what that tells me is, downstream of this, before pruning, it split on those variables, and they got rolled up into the linear model, but not into the splitting criteria. That doesn't have any particular significance, but you might look at this and say, well, geez, the ruling has 2 things in it, and it has other things in the linear model. They don't have to be the same. Okay. The second rule, so this covers 58 cases. The second rule covers 126. Again, there's a bunch of zip codes, and baths greater than 2. And so, and then you can see the linear model there has many in the same terms, but it has a term for baths, and that's one of the main differences. So there's 8 total rules. I don't want to print them all out and bore you guys with them. I wouldn't say this model is terribly interpretable. I mean, maybe if you had 2 or 3 rules and the linear model wasn't excessively complex, then you might be able to gain something from it. But it's pretty close to a black box to me.
So beds comes in negative in the second model?
I'll get to that in a second. So we have 2 plot methods on here. The first one, if you just do a dot plot of this, what it does is for each rule and for each predictor involved in the rules, it kind of gives you a sense of where it's split. So the x-axis here is not the actual units of beds and square footage. It's actually scaled down to percentiles. So the first rule involves zip code, which I can't really represent numerically here, but it involves beds. And so you can see this is 1 bed and 2 bed. The second rule, if you remember, was beds greater than 2, I think, and that's represented here. So you can kind of see that the first rule involves beds, and the second rule involves beds, and the third rule involves beds. And the second and third rule cover beds the same way, but would have different linear models. And then the rest of the rules don't involve beds at all. And then you can see here that square footage is not involved in the first rule, but it's involved in the other ones. And in the sort of reflective pattern here, where you have this and the complement of that, is fairly typical. And I think that happens, I know that happens because when you split on a tree, one split goes less than or equal to 2 beds, and the other goes greater than or equal to, and that pattern gets sometimes preserved in the rules. So then the other plot you can do is you can plot the coefficients. So yeah, so this kind of stands out. So it works. I don't know why. So with the exception of the first rule, which has a large positive coefficient, large-ish positive coefficient for beds, all the others are negative, which means the more beds you have, the less your house is going to sell for. But that's in combination with zip code, with baths, with longitude, latitude, and square footage. It predicts really well on test data and everything else. But I look at that and I'm like, why would you be penalized for the number of beds in your house?
Could it be a proxy for like multifamily?
I have no idea. No idea. All right, so that's the plot method. There's a predict method when you want to predict your new samples, and it produces things pretty nicely. What do you want to time? Okay, I'm kind of behind. So the boosting-like procedure, he calls it committees. So imagine you fit your first model tree, and you go to predict a value, and let's say the value is 100, and you predict it to be, let's say, 200, okay? So what it does, boosting traditionally would adapt the weights of your samples to emphasize certain prediction or certain samples in the next model. That's what most boosting procedures do, is they adapt the current data set by use of case weights to make the model go after those samples that you've missed with more rigor, okay? Committees kind of do the same thing, but they take it on the other side of things and they adjust the outcome. So the outcome, all the case weights and everything stay the same, but when you fit a new tree in a Cubist model that has this boosting-like procedure, you use this as the new outcome. So what you do is you take 2 times the last prediction, or the current, the last actual outcome value, and subtract off the prediction. So back this up. So my data point is 100, okay? I predict it to be 200, right? So using this, I would take the data point is 100, so this would be 200 minus 200. So in the second model, I replace the outcome for that data point as 0. So what it's doing is if I'm over-predicting on that sample, it's taking the outcome and adjusting it away from the prediction so that the model will then under-predict it next time to balance things out. Okay? So it doesn't do anything weird with case weights. It doesn't do, it does weird things with the outcome. But every outcome in Cubist, as you fit these committees, the actual outcomes are different. But the predictions still get used. So it's trying to force the model to go in towards the real value by sort of tilting the original data point in a direction away from where you made the error. It works. If you want to do this in R, the code's the same. You would tell it how many committees to use, which is how many iterations of boosting. This definitely takes a model that was not really interpretable to begin with and makes it really a black box. Because what happens if you do, let's say, 50 committees, you're averaging 50 models. Now don't forget, each one of those models might be really deep, and in each prediction might be the average of many, many, many different linear models in that tree. So you might actually, depending on how your data size is, how many predictors, you might be averaging millions of models at some point if your data is deep enough and you have enough predictors and enough boosting iterations. So it's basically smoothing the crap out of these models. But it tends to work. So if you look at, this is again using cross-validation, all the things being equal, if I look up to 35 committees, and again, this is the model with factors, and that's the model where I have dummy variables, you can see performance really improves especially here, that even on the first or second iteration of committees of boosting, I'm getting a really big drop in my error rate. So this additional smoothing it's doing through these committees is having a really positive impact on my model prediction. And my experience is where sometimes when boosting you have to fit thousands of trees, the actual software only goes up to 100 committees, and I've never really seen it pick anything, or I've always seen it converge after like 20 or 30 committees. So you don't have to do very many iterations of this to get the full effect of it. You won't be fitting thousands and thousands of committees. So it tends to be relatively efficient in doing that. Okay. So then the other aspect of Cubist that separates it from model trees is, and he published this in '93, where he does this nearest neighbor adjustment. So whether you're fitting a committee or a single, let me just do this to mess with the guy. Whether you're fitting a single model tree or a committee of models, what happens at the end of that is you get a model-based prediction. But at the time of prediction, you have the option to average that model-based prediction or adjust that model-based prediction using nearest neighbors of your training set. And the way it does it is, let's say you say I want to use, let's say, 3 nearest neighbors. The first thing it does is when you go to predict a new sample, it finds the nearest neighbors and it creates weights for those nearest neighbors based on distance. So neighbors that are very close by get heavy weights, whereas neighbors that are far away get low weights. Okay? And it has a cutoff for the weights, so you can't have something that's really far away used here. And so what it does is it takes when you take that model and predict the closest training set point, you subtract that from the actual training set point. Okay, and then you add your model prediction to this. So this is what you would get normally, this y hat here. And then for every neighbor that you ask it to look at, it does a weighted average of them based on this little adjustment with the training set samples. Okay, and so what I've experienced is this can also have a really, really profoundly positive impact. It does something interesting, and I've kind of come to rationalize why that is your performance without neighbors, the neighbor-based adjustment might be here. When you do the first neighbor-based adjustment, let's say lower is better here. Using one neighbor makes the prediction sometimes really bad because it's overfitting to that one data point with the neighbors. And then as you start to add more neighbors using the adjustment, it tends to get to where the original model would have done and then surpass it in performance. So it's not uncommon to see if you tell it to do one nearest neighbor adjustment, it does really poorly with that because I think it's overfitting to its nearest neighbor. So anyway, that's just what I've experienced. You can fit whatever Cubist model you want, whether it's committees or not, but once you get that, you don't have to tell it how many neighbors to use, if any, until you go to do prediction. And so this would be the code when you go to predict new samples. You would say, hey, give me 4 neighbors, don't do any neighbor adjustment, and so on. So I'll get to that code in a minute, but here's what it looks like in the same sort of cross-validation scheme. So these are the same number of committees. There's 0 here, which one is hard to tell, which is the red one, which is in this group here and over there. That's a 0 neighbor model adjustment, so that's the same curve I showed you before. And then you can see what happens is I add 1 neighbor and performance gets worse. And then I get 3 and it goes down, and then you can see maybe around 9 it optimizes. So it's smoothing, it feels like just the right amount at that point. So it's smoothing on 1 neighbor, it overdoes it, the correction, and does poorly. And again, if we were to look at this just at the last iteration, we can see there's a real effect here, that going from maybe 1 neighbor down can have an effect. It's sometimes bigger than what's shown here. But anyway, you can see how the neighbors affect things. So this is kind of like an early ensemble method that uses, a combined model prediction with a neighbor-based adjustment. So to do this, if you wanted to tune over the committees and neighbors, because each one seems to have an effect, you could use this CARET package, and what you would do is you would give it a grid, and it can figure out it for you if you don't want to go to the trouble of doing it. But you can tell it how many committees to evaluate, how many neighbors to look at, and then you can put it in here and let cross-validation figure it out whether you should use 20 iterations with no neighbors or 3 neighbors. And so fitting the model in this way generates plots like this where you can look at cross-validation results on your model and see how many iterations or how many committees should I use and so on. Okay. So we have a little plug for that. All right, so here's how well it does on the data we're looking at. And you can see the error bars here are based on cross-validation. So I did, I think, 5 repeats of 10-fold cross-validation. So this is the cross-validated estimate and its associated error based on the resampling results. And the red dots here are the test set result. And you can see, and I just did them by the overall average results. And so if you look at the cross-validation, a boosted tree using dummy variables does better, slightly better than Cubist and cross-validation, but the tested error is much, much lower, I think, proportionally to what a boosted tree would do. So I find these two are typically in the running for the top spots in a lot of the models that I fit. And you can see how some things do, like a card tree is like, it's awful in this particular instance. And you can see what other models tend to do. So we have radial basis function support vector machine, random forest, k-nearest neighbors. Cubist, this is with the dummy variables, and this is with letting it use the factors. And so that worked better. Weirdly, for GBM, this is it using factors, and this is it using dummy variables, and it liked dummy variables more. That's a separate talk. But so that's what it was for this Sacramento house price data. What I also did is, in the book, we do similar things. And this is another regression model based on data compressive strength of concrete. And again, we fit a bunch of models. The top 3 here were Cubist neural networks, again, and boosted tree. The boosted tree did better than the Cubist model, but you can sort of see the pack forming down here. And we also have some computational chemistry data in the book. And so we're trying to predict solubility. So here's the test set in orangish, and the red circles, the cross-validation, and again, Cubist down here, along with support vector machines, did very well. Now, there's this great paper written in, I think, the 80s that was called The Illusion of Classifier Improvement, where everybody says, anytime you see somebody publish with their model, it's always the best model. And one of the reasons for that is they know so much about their model, and they treat it preferentially because they tune it really, really well for that data set, whereas the other models, like, I'll throw it in random forest. I tune the crap out of all these models, so you have to take my word for it. And you can look at all the code for this. None of these, k-nearest neighbor model's not doing poorly because I only tested on a few neighbors. So these are fairly, I think, unbiased representations of how well the model works.
What was the data quickly, did you say?
In this one?
Yes, APM solubility.
So APM is applied per combined. It's a book that we wrote. Sorry about that, I should have said that. And then solubility is a public computational chemistry data set where we're trying to predict solubility of molecules based on their chemical structure. And so we took that data, and in the book we go through that as an example for all sorts of different models, and these are sort of the results from that. Yes?
When does Cubist not perform well?
Well, it's hard to answer because my answer is I've never seen it really tank. Like, I've never seen it do horrible. I mean, the same way I've never seen random forest really tank. I've never seen it at the bottom of the list. It's surprising, I want to say it's surprising that it doesn't overfit, but given the amount, I think I've hopefully demonstrated this is smoothing the bejeebies out of every model you can possibly fit to these data. So it probably wouldn't overfit in that respect. I haven't been able to figure out any patterns where if the true boundary is linear, it would do badly. I have another data set that we'll have in our next book, and I don't want to release the data yet, but it's a situation where I find straight up linear models do really well. And Cubist does it right there with them. It's maybe not as good as something like the Glim net, but at the same point, it's not, if you did that with, let's say, random forest, you would get penalized because of the regression to the mean. So that's a situation where random forest doesn't do all that great, but Cubist is right there with the linear models. Probably because it only fits 1 or 2 linear models and doesn't have the chance to overly do things. So even when, it's a highly nonlinear model, but even when the actual underlying relationship is linear, it still seems to not overdo it. So I don't want to say it's perfect by any means, but I've never seen it really fall on its face yet. Yes?
So how stable are the rules if you, say, try a few different random seeds in your initial training selection?
I don't know that I don't know. My intuition is that they're not stable from the sense of repeatable, but they're stable from the sense like CARET is, that if you do it enough times, it doesn't matter. Right? So it probably suffers from the same instability that any other individual tree suffers from. If you change the data a little bit, the split goes differently. But again, it averages so much down the line that I think that's its saving grace. So what I guess my answer is, yeah, the rules are probably unstable. They'll be different if you shuffle or jitter the data a little bit. But I don't know the prediction's going to fail so much under those situations. So interpretability-wise, it's not stable, but prediction-wise, it most likely is. Yes?
When is it an advantage to use a decision tree over random forest, and when is it an advantage to use random forest over Cubist?
So, there's no free lunch theorem, so we can't say, irrespective of anything, any model's any better than the others. Random forest, I think, always does pretty well, right? I mean, I think that there's a lot of evidence for that. I have a lot of situations where, especially with either linear class boundaries or highly imbalanced data, where straight up simple random forest does worse, let's say, than logistic regression. So that would be an example where random forest maybe doesn't do as well as you would expect it to do. Compared to a tree, I've seen papers and I've seen evidence where bagging and random forest do worse than an individual tree, but I've never experienced that. So I know, like Quinlan wrote a paper way back in the 80s about bagging and boosting, and he actually has one of the UCI data sets. He shows that my just simple single tree is better than bagging or random forest. I've never experienced that. I don't want to say it won't happen, but I don't know why that would happen. And then what was the last one? Random forest versus
Cubist.
Cubist. I mean, again, Cubist to me is the reason I would go to Cubist before random forest is when I want to predict the tails really well. So I know it's going to do better than random forest than that. I just know it is because experiences show me that, and theoretically I know that's most likely the case. So if you're managing like a big database of your customers and you want to find the most lucrative customers, right? You want to get that tail of the predictions right. You don't care if I mispredict the people don't spend much money. The same way, so I work with Pfizer in drug discovery. We don't really care if our inactive molecules are wildly mispredicted as long as they're still at that tail. But the ones that are really active, well, we make damn sure we get those predicted well. And so those would be the cases where if the quality of prediction that is most important to me is very localized in a particular area, especially in the tails, that I would probably do something other than, let's say, random forest or boosting. And Cubist seems like a good alternative there because it has that smoothing of linear models. It's immune to that. Yes. Wait, there's somebody over here, right?
I just wanted to comment on the
I think he was yawning. Go ahead.
Could you expand on the comment about the tails and how Cubist actually works? I mean, can you go out of the boundary of what's in the data set in terminal nodes because of the regression model?
Yeah. So again, Cubist in your terminal node, Cubist has the ability, since it's a slope intercept model in the terminal node, to predict at the extremes of your observed data or beyond. Now the thing is, and I implemented this in CARET. He also has a thing in there where he estimates reasonable ranges of predictions.
So he limits them, essentially.
You can.
Something that limits.
Yes, he has code in there that it won't predict things that are wildly extreme. Like Mars will do this sometimes, multivariate adaptive regression splines. When I go to predict test set, sometimes I'll get predictions that are like 5 or 6 orders of magnitude off of what the prediction is, and that's because of the way those basis functions work. So that's why I put it in CARET, where you have the option of limiting the prediction within a certain range of the data set. We don't do that automatically, but he does have that ability in there. Yeah.
Is there any work on trying to use the model to get a sense of what predictors are more important than others?
Yeah, so he does have things in there where he looks at, he counts up the number of times predictors were used in splits and in the linear model. So he gives you count statistics on that, and if you ask for variable importance, we have kind of like a weighted average of that. That's not terribly informative. You would think that you could do that because a lot of what he does is, I fit a model with that has this error rate, and I fit a model without some term with that error rate. So he's making a ton of decisions in the source code based on, it's not like a likelihood ratio test, but the math is kind of the same. He's doing it millions of times, right? So there is the ability, like you would in random forest and other places, to monitor that drop. If I get rid of that variable, how much of things get worse. So it's in there all over the place, but he doesn't really accumulate that or average that. So theoretically, yeah. but in actuality, he doesn't really track that. Yes?
Can you comment a little bit on the efficiency on the model building, depending on your observation set, like how big, columns?
So we run, I said to somebody, we predicted billions of molecules with this model.
On the training set or on the scoring set?
On the scoring, but many of our computational chemistry models are Cubist models, and they get automatically updated a lot of times. And we've never had a situation where Cubist couldn't do it. So now this is a Cubist R package, so you're bound by what R can do. But you can go to his website and download the GPL version of this. This is all based on C code, the command line. And I don't want to say it's limitless, but he's extreme. He's running C code in the 80s and 90s. And me, I'm lazy because I'll say, oh, memory will get bigger, right? Right? He didn't have that, so he's extremely efficient about his code. Like when he does the neighbor-based calculation, he fits a KD tree. It's Manhattan distance, I believe. So it's extremely efficient. It doesn't have to hold a ton in memory. So it's not it's not magic or a miracle, but it's tight code. Yes.
What's your recommendation for high cardinality variables if you're using Cubist? And why are the predictions different when you use factor variables compared to if you break it down to the dummy variable?
So I got the second part of the question, but I didn't get really the first part.
So if you have a variable that is suffering from high cardinality.
Oh, so like collinearity and stuff? Cardinality.
Cardinality.
Oh, okay, sorry. So a lot of trees are biased in the sense that they'll split. They're more likely to split on predictors that have many values. I know his tree-based models are resistant to that because of how he computes the splitting criteria. I don't think that these are immune to that the way C5 and other models are. Like CARET really suffers from that. C4.5 and C5 don't because they account for that. I don't know, I would assume he does, but I don't remember seeing anything that accounts for that in the splitting criteria. So I would say they probably are susceptible to biases, splitting biases like other trees. And then I don't remember the second question now.
Why the prediction varies if you use factor variables?
Oh yeah, I don't know. So I've been thinking about this for a long time, and I just got done a few days ago running a ton of simulations where I took a lot of different data sets, varying levels of factors in them, and fit the same exact data with factors and without factors. And I shouldn't say stay tuned later, but so you'll come to that talk. But basically what I found was it's really inconclusive. I have some data sets where it matters a lot. I have many data sets where it doesn't matter. I can think of why that might be. So if I have let's say it depends on the pattern. Right? So if the pattern is where I have, let's say, one of those categories is hugely important and the other are about the same, I could imagine dummy variables doing much better because it has to do one split to get that. But maybe the factor-based splitting would do the same thing just as well. I don't know. I could just think of situations in different data sets where one might be optimal, whereas the other might not be. So the one case where it seemed to matter a lot is a data set that's on UCI where all the predictors are categorical. And I see the factors have a clear edge in that instance. To varying degrees with different models. So I tried with like 10 or so different trees and rules and all sorts of boosting, not boosting. And for all the other data sets, like this one showed a little bit of a difference here. But for the most part, they didn't show a difference. But the one, the UCI data set, really did. Now the one definite conclusion I can make, and this might be implementation dependent, is my assumption would be that knowing how these things handle factors, some of them would go to very complicated algorithms to figure out how to do a binary split of a factor. And I thought, wow, that must really slow things down. If they have a bunch of dummy variables, it's like boop, 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 right? It should be able to go. It's the opposite of that. That uniformly, the time it takes to fit these models using factors is almost always order of magnitude better than using the dummy variables. Which must mean that the number of dummy variables that are getting generated overwhelms, even though that's probably a faster operation, there's probably so many more of them, the total time takes longer than just valuing the factors. So that's one definite thing I can say, but I'm trying to pin it down to where it could be, if you have a model that's like getting 99% accuracy, I can imagine, well, it probably won't make a difference there because it's an easy problem, right? So it's a complicated, it's an easy question to ask, and I've been asking myself, but I keep thinking about, well, it really depends on a bunch of different things, and the more experiments I do to try to figure this out, the more I'm confounded by why it would be that way. So I just have to say, like, you know, it's kind of like asking, like, you know, why does a random forest work the best for everything? Because there's some data sets that are more conducive to a support vector machine or a logistic regression. And sometimes you can figure out why that is. But in this particular instance, I can't find any pattern or any instance that would say, oh, right, that's why it does better than dummy neurons. To this point, I really don't know. Any other questions?
Sorry.
No, go ahead.
Continue roboting with. Has there been any sort of, what's your experience been with using or adapting Cubist to more of a classifier as opposed to more of a regression kind of predictor?
Right, so people try to do that. So the Java, like the Weka people did that. I haven't used that code. I don't know. I think it's like putting makeup on a pig. I think it's like, well, that's not a good analogy because Cubist shouldn't be used as a pig in this. You know, but it's like maybe a square peg in a round hole. I mean, all the splitting criteria and everything is really optimized towards regression. And I think you would have to do invasive surgery to change that out. Many of the things that are in Cubist, not the linear models in the tails, but many of the concepts of what it does. So C5 is the analogous model that he built for classification, and that's a fantastic model. That model is just as good as Cubist. And so for me, that does just as well as Cubist does for regression. There are other models that people have done where they have linear models and tails, and again, you can use those for classification or whatever it is you want. I don't think they're as powerful because the ones I've seen, the way they do the splitting criteria, like you have to define these variables for splitting and these variables for regression, and predefining that to me doesn't seem to work as well as letting the model figure it out. So I have a feeling that having like a logistic regression in the tails is probably, there's gold in those hills, right? That would theoretically do really nicely on a lot of problems, but I have not seen an implementation or a lot of publishing on that to really make an informed decision. I probably wouldn't try to back, reverse engineer cubes to do that because it's really hyper optimized for regression.
Thank you.
You good fit?
Anybody else?
Well, thanks, Max.
Thank you. Any of those over?